Hello students, welcome to GTQ 2024 session. In this session, I am going to explain important questions which are expected in GATE 2024. Right? Subject title, Computer Organization and Architecture. As you know my name is Sagar Pingili. Right? Here I am going to explain expected questions in GATE 2024 from the subject Computer Organization and Architecture. All right. This is the first question. All of you just see the question once. Consider the following format. This is the floating point format given. Sign 1 bit, biased exponent 6 bit, mantissa 9 bit. Which of the following represents the value greater than 16 base 10? So we need to identify the options which are greater than 16 in decimal format. Right? So this is the question. Here 4 options given. Now you need to decide which option is greater than 16. Right? Fine. So what is the answer? Format given, binary codes given. We need to identify the option which is greater than 16. First, take the first option given. A 0 1 0 0 0 1 1. Next 1 1 0 1. Remaining all zeros. Yes, this is the A option given. Now we need to identify, is this option greater than 16 or not? So convert the given binary code into equivalent decimal value with respect to the given floating point format. So in the floating point format, 1 bit is allocated for sign, then 6 bits are allocated for BE, and 9 bits are allocated for mantissa. Okay, now report the value. What is the value here? So value is equal to plus or minus, value is equal to minus 1 to the power of S into 1.m into 2 to the power of BE minus bias. This is the straightforward formula which describes the value which is associated with the given floating point binary code. Okay, so minus 1 to the power of S0 1.m 1101 00000 into 2 power BE. What is the BE value? See this? This is 1, 2, 4, 8, 16, 32. Right? This is total 35. BE value 35. So 35 minus bias. Bias. What is the bias? Bias depends on the format. So here this is the 6-bit BE. 6-bit BE normal bias. So normal bias is by default normal bias is equal to plus 2 power 6 minus 1 minus 1. Right? So this is equal to plus 31. 31 is the bias of the given format. Right? So now take it. 35 minus 31. So this is plus 1.1101000000 into 2 to the power of plus 4. Okay. So now to report the decimal value, we are going to shift the data to left direction 4 times. Then this exponent becomes 0. So plus 101.00000 into 2 power 4 minus 4. You know, for every left shift, exponent is decremented. When this data is aligned to left direction 4 times, okay, exponent is decremented 4 times. Now exponent becomes 0. Right? Now report the decimal value. If you see this decimal value is greater than 16. This value is greater than 16, correct? 1, 2, 4, 8, 16. So this value is greater than 16. Therefore, option A is matching. Option A, binary code, is greater than 16. Okay. Now go to the option B. Here option B given. What is option B? B is 0, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0. Remaining all are ones. Right. This information will be placed into the given hypothetical format. Okay. Sign, biased exponent and mantissa. Alright. So now we need to report the value. So value is equal to minus 1 power of s 1.m into 2 power be minus bias. Correct. So minus 1 to the power of 0, 1.0010111111 into 2 power be. Be value, this one. So 1, 2, 4, 8, 16. Okay. So that is equal to 30. Bias is 31. So this is plus 1.00101111 into 2 power minus 1. So we need to make this exponent 0. So shift the data to right direction one time. So plus 0.10101111 into 2 power minus 1 plus 1. Okay, this is cancel. So if you see this value is compulsory less than 16. Okay, question is expecting the greater than 16 equivalent code. So this code is less than 16. So this is not matching. Now come to C. C option. What is given? Given code is 0, 1, 0, 0, 0, 3 zeros, 1 0, right? 4 zeros. Next 1, 0, 0, 1, 1, 1. So when the question contain binary code, compulsory you need to take care about the given binary sequence. Okay. So clearly take the given binary sequence. If any wrong is injected while copying the given binary code at the time of solving the question, okay, even you know the concepts, because of wrong data is copied, your answer is wrong. So that's what, when question contain the binary codes, okay, you need to take care about the given binary codes, right? Fine. So now 1 bit sign and 6 bits BE and remaining bits are the mantissa, correct? So now value you know. So minus 1 to the power of 0, 1.0000 1001111 into 2 to the power of BE. What is this BE value? 1, 2, 4, 8, 16, 32. So this becomes 34. 34 minus 31. Okay. So this is plus 1.0000, okay, 1001111 into 2 to the power of 3. Right? So now make this exponent 0, shift the data to left direction 3 times. So plus 1.000.01001111 into 2 power 3 minus 3. Exponent cancelled. Okay. So what is this value? This value is less than, this is 8 point something. So this is also less than 16. So we want greater than 16. So this is wrong. Right. So what is the last option? D option. When you take D, given binary code is 0, 1, 0, 0, 1, 0, 0, then 0, 0, 1, 0, 1, 0, 0, 0, 0. So this is the binary code given. Interpreting given binary code into the format. This is the format. Sign 1 bit. This is sign. This is BE and this is mantissa. Correct? So now what is the value? Minus 1 to the power of 0, 1.0010 into 2 power BE. This BE value 1, 2, 4, 8, 16, 32. This is equal to 36. Okay, minus 31. BE minus bias. So this is plus 1.00101000 into 2 power 5. 36 minus 31, 5. So make this exponent 0. For that, align the data to left direction 5 times. So 1, 0, 0, 1, 0, 1, 5 times 0.0000 into 2 power 5. Because of left alignment 5 times, exponent is decremented 5 times. So exponent become cancel. Now report the decimal value. So this decimal value 1, 2, 4, 8, 16, 32. So this is greater than 16. Okay. So this D option, binary code equivalent decimal value greater than 16. Okay. C option, binary code equivalent decimal value less than 16. B option, equivalent decimal value of the given binary code less than 16. A option, equivalent decimal value of the given binary code is greater than 16. Now what the question says? Which of the following represents the value greater than 16? Okay, here 4 options given. In the 4 options, 2 options are matching to the given information. Okay, what is the answer here? Answer is A and D. Okay, this A value is greater than, this A value is greater than 16 and D option value also greater than 16. So correct answer is, here answer is A and D. Students, I hope you understand the analysis of this question. Okay, how many of you are given the right answers? Let me know. A and D is the right answer. How many of you given the right answers? Verify the solution. Very good. All right, dear students. Now we are move on to the next question. Yes, this is the next expected question from the floating point data representation topic. Okay. Question is, consider the following format. Sign, biased exponent, mantissa. This is the hypothetical format given. Right? Sign 1 bit space allocated, for BE 5 bit space, mantissa 10 bits space. Which is the hexadecimal equivalent in the memory after adding the following data? See this. Here we are going to perform the addition operation after adding the following data. So this is the data. Let us say First data is x, second data is y. So two data elements given. We need to add these two numbers. Okay. After adding the given data, that result will be stored into a memory by using the given floating point format. Okay. So that result is expected in the hexadecimal format. Okay. So which is the hexadecimal equivalent in the memory after adding the following data? This is the question. Okay, please solve the question. Let me see the correct answer from your side. Okay, right. Let me see how many of you giving the right answer. Parallelly, I am also going to solve the question. Okay, you also please solve the question. Okay, at the end, we are going to match the answers, compare the answers. So, okay, whether your answer is matching to my answer or not. Okay, that we will decide. Okay, start the analysis. I am also solving the questions in parallel. Very good. So here given is hypothetical format given. Sign, biased exponent and mantissa. So this is 1 bit sign, 5 bits BE and 10 bits mantissa given. Okay. So here bias, default normal bias. Normal bias value is equal to plus 2 power n minus 1 minus 1, that is 5 minus 1 minus 1. This is equal to plus 15. Alright, this is the bias. Then there are two numbers present. Given numbers are 2. First, x given. Okay, 1.1011001000 into 2 power plus 8. Y 1.00101 then 0000011 into 2 to the power of plus 4. Correct? Yeah, this is the given information x and y. Now we are going to do the addition operation. You know the procedure to perform the addition operation between the floating point numbers. What is the procedure? First take the two numbers x and y, and next we are going to compare the exponents of the given numbers. When both the numbers exponents are equal, directly we are doing the addition of the mantissas. Okay. When both of the numbers exponents are not equal, then identify the difference. Okay. Based on that difference, take the smaller exponent mantissa, align that mantissa to right direction up to the difference to make the exponents equal. After equalize the exponents, perform the addition operation between the mantissas. Then do the normalization and store the result into a memory. This is the procedure for the addition operation. Everyone knows that. Okay. All right. Now apply that procedure here. Apply the procedure. Right. First, in step, already we have x and y values. And second, compare the exponents. Okay. 8 is the exponent of x, 4 is the exponent of y. Both are not same. Now take the difference. 8 minus 4. This is equal to 4. Okay. Exponent difference is 4. Clear? So when exponent difference is 4, take the smaller exponent mantissa. So y 1.00101000011 into 2 to the power of plus 4. Now this data will be aligned to right direction 4 times. So 0.0001 0010 1000011 into 2 to the power of plus 8. Yes, this is the data after the alignment. Take the smaller exponent mantissa, align to right direction up to the difference. Okay, so now after equalize the exponents, take the exponent common, do the addition operation between the mantissas. So x mantissa is 1.101100, okay, 1000. Then y mantissa is 0.0001, okay, 0010, 0010, 1000, 1000, 11. Yes. So x mantissa, y mantissa. Verify once again. X mantissa 1.1011001000. Done. Y mantissa 0.00010010. Okay. 100011. Correct. Now do the addition operation. 11000100 1.1. This is the result. X plus y. Mantissas are added. Now take the final result. Final result is sign is positive. That is final result equal to 1.11000100010011 into 2 power plus 8. Yes, this is the final result. Is it clear? All right. So now this result is already present in the normalized format. When the data is present in the normalized format, directly we can store the data into a memory by using the floating point format. Okay. Now storage. So here sign is positive. When sign is positive, binary code is 0. Second, BE is equal to AE plus bias. Okay. So actual exponent is 8. Okay. So 0, 1, 0, 0, 0. This is the 5-bit code. Then bias 0, all ones 15. Now adding 1, 1, 1, 0, 1. This is the BE. BE value ready. Then mantissa. Mantissa is already available. This is the normalized mantissa. See, mantissa 1.11000100100011. Yes, this is the normalized mantissa. Now we need to keep this information in the given floating point format. Okay. Right. Sign positive 0. BE 10. Okay, 111. Next, mantissa. Mantissa only 10 bits space is allocated. Okay, so only 10 bits we need to consider. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Only 10 bits space is allocated for mantissa, so that 10 bits fraction we need to take and remaining fraction need not to store. Okay, so 1, 1, 0, 0, 0, 1, 0, 0, 1, 0. Yes, this is the mantissa. Okay, so after addition, result will be stored in the memory by using the given floating point format like this. Okay, now we need to report the hexadecimal. When you want hexadecimal, group 4 bits. Report the value. 4 bits, 2, 4 bits, 1, 4 bits, F, 4 bits, 5. So 5F, 1, 2, base H. This is the answer. This is the answer. Okay, after performing the addition operation between the given two floating point numbers, result will be stored in the memory by using the floating point format. That equivalent hexadecimal value is 5F12. Okay, now go back to the question, select the correct option. 5F12. Yeah, this is the question. In this question, right answer is what? B. 5F12. This is the answer. Answer is B. Dear students, let me see how many of you given the right answer. Okay, I ask you to solve the question along with me. Okay, I solved the question. In parallel, you also solve the question. Okay, whether your answer is matching or not matching, please compare with this analysis. So right answer is B. All right. Students, read the question. In which of the following cases overflow condition will be occurred after adding the following signed data? See, they given the signed data. Signed data by default 2's complement data. Okay, after adding the signed data, in which of the following cases overflow condition is occurred? This is the question. Okay, 4 options given. We need to do the addition operation. After addition operation, in how many cases overflow condition occurred? Overflow condition means range exceeding condition. Okay, as you know that range exceeding condition will be occurred in the signed numbers with 3 different representations. Okay, first, if you want to specify the range exceeding condition, we have a plain text condition. What is the text here? There is a carry into the MSB and no carry out of the MSB or vice versa. When this condition is true, overflow set. When this condition is false, overflow reset. Okay, that is the plain text related condition. And second way to represent the overflow in the signed arithmetic is XOR operation. XOR operation between the in carry and out carry with respect to MSB. Okay, so XOR operation between the in carry and out carry with respect to MSB is the overflow. And third way to represent the overflow is when the same sign data is processed, result contain opposite sign, then overflow occurred. Okay, so we are going to represent the overflow condition in the signed arithmetic in 3 different ways. One is the plain text representation, second is the XOR operation, third is the sign point of view. When the same sign data is processed, result contain opposite sign, then overflow present. Okay, so you may take any one of the method to represent the overflow after performing the signed arithmetic. Okay, right. Please solve the question. I am also solving the question. You to solve the question along with me. Finally, we are going to compare the answers. Okay, if your answer is matching, then your analysis is correct. Otherwise, you please verify your analysis once again where you did the mistake. Okay, all right. Now see this. Here we are going to take the addition operation. 0, 1, 1, 1, 0, 1, 1. So what is the condition of the carry? MSB. This is negative sign, negative sign. Same sign of the data processed. Result contain same sign. Then overflow become 0. Overflow flag is equal to 0. Reset. That means range is not exceeding. Okay, because same sign data is processed, result contains same sign, then overflow not present. Right? Overflow present when the result contain opposite sign. Okay, when 2 negative numbers are processed, result contain positive sign, then overflow present. When two positive numbers are processed, result contain negative sign, then overflow present. Okay, so in this case there is no overflow. Now come to the B option. So here see 0 1 1 1 0 1 1. Right, now if you see the MSB, this is negative, this is also negative, result is also negative. When same sign data process, result contains same sign, then overflow flag is reset. So here also overflow flag is 0. All right, now come to the option C. This one 1 0 0, right, 0 1 0 1. Now when you see the result, first operand MSB bit is negative, second operand MSB bit is negative, result MSB bit is 0. When same sign data processed, result contain opposite sign, then overflow present. So here overflow flag equal to 1 set, range exceeding. Now come to the last one. In the last one 1 1 0, just doing the addition operation 0 0 1 carry 1. Okay, now again compare the values. MSB bit of first operand is negative, MSB bit of second operand is negative, MSB bit of result is also negative. Okay, there is no opposite sign. That's what overflow flag is 0. Okay, in the given 4 options, overflow condition is set in the C option. Okay, A option there is no overflow, B option there is no overflow, D option there is no overflow. Overflow present in the option C. Therefore correct answer is, here answer is C. I hope you understand the analysis. Okay, most of you know the overflow condition, so that you all are giving the right answer only. So answer is C. Okay, please verify your answer. How many of you given right answers? This is the question. All of you please read the question. Consider the following system configuration. 16-bit CPU, 2 power 48 bytes of RAM. Okay, 2 cells interfacing. There is an interfacing between the CPU and memory. This concept already known to you, because CPU data type is word, memory data type is byte. Okay, CPU always expecting the data from the memory in a form of words, so that memory interfacing will be adjusted during the design time of a computer according to word length of a CPU. So here it is a 16-bit CPU, cell size is 8-bit, that's what 2 cells are interfaced. Okay, so when CPU refer the memory, at a time 2 cells information is traveling. Okay, so when 2 cells information is moving from memory to CPU, okay, CPU getting the 16-bit data. Okay, so that memory physical structure is byte wise, accessing sequence is word wise. This is the concept of a computer system design. Everyone knows that. Very good. Instruction is designed with to address format. So here instruction is a to address instruction. In this system, instruction designed with to address, where address 1 uses direct addressing mode, address 2 uses indirect addressing mode. Direct addressing mode, indirect addressing mode. Okay, opcode is designed with 1 word long. So opcode size given 1 word. With data transfer operation. So here opcode is a data transfer operation. It may be move operation, or it may be load operation, it may be store operation. Okay, so data transfer operation associated with the opcode. Address 1 is used as a destination and address 2 is used as a source. Yes, this is obviously true. Standard syntax of the machine instruction is first opcode, next destination, next source. That is the generalized standard syntax of a machine instruction. Alright. Number of memory references required. Number of memory references required to complete the instruction. To complete the instruction. To complete the instruction means what? Fetch the instruction from the memory, execute the instruction. So fetch cycle plus execution cycle. Okay, together how many memory references are required? That you need to identify. Okay, all of you please solve the question. Let me see whether you giving the right answer or wrong answer. This is the one important question, nice question. You please solve the question. Do it fast. Especially when we have the indirect addressing mode. Especially when you have the indirect addressing mode, address size is matter. Indirect addressing mode point of view, address size is important. Very important. Reason is what? When you are going to fetch the effective address from the memory, indirect addressing mode means effective address is in the memory. To fetch the effective address from the memory, address size is playing very important role. When the address size is one word, one memory reference is required to get the effective address from the memory. If address size is 2 words, address size is 3 words, then number of memory references varies. Okay, that's what when the question contain indirect addressing mode, compulsory we are going to take care about the address size. Okay, all right. This is the question. Please solve the question. Okay, right. Instruction completion. That means what? Fetch cycle and execution cycle. Okay, so fetch cycle is connected to execution cycle. After execution cycle, control is moving back to fetch cycle. Okay, so this is called as the instruction cycle. So completion of the instruction means instruction cycle. We need to identify. This is the instruction cycle. Okay, all right. If you see the instruction cycle, what is the framework we have analyzed in our regular class? IF, ID, OF, PD, WB. These are the instruction execution states, as you know. OF, operand fetch, source 1, source 2. WB, write back, destination. This is the framework of the instruction execution sequence. Everyone knows this. Now interpret the given instruction into this format. Then automatically you may understand the number of memory references required. Okay, all right. So what is the instruction here? Instruction is a to address instruction. See this. Okay, opcode to address format. Opcode, address 1 and address 2. This is the to address format. All right. So what this opcode indicates? Type of operation. They given data transfer operation. In the question, they said it is a data transfer operation. Now address 1, according to the question, they indicated as a destination. Okay, address 2 according to the question indicated as a source. Is it clear? All right. So now address 1 uses direct addressing mode. Then address 2 uses indirect addressing mode. Okay, see that. So here that is mentioned clearly. Address 1 uses direct addressing, address 2 uses indirect addressing. Opcode is a data transfer operation. Then what is the size of the opcode? 1 word. What is 1 word? 16 bit. Alright. Then what is the address size? Address size 2 power 48 bytes. That means 48 bit address is present. 48 bit. Okay. How many words? That is 3 words. Right? Okay. So come to this. So according to this question, opcode size they given, see this, 1 word opcode. Question clearly mentioned this. Then address size is 48 bit. This address size is 48 bit. Very good. So 48 bit means according to the CPU, 16 bit CPU, this is the 3 word and this is also 3 word. Okay, with respect to 16 bit CPU, word length is 16 bit. So that 48 bit means 3 words long. Therefore, here total instruction size is equal to, okay, 331. That is 7 words. Opcode is 1 word, address 1 3 word, address 2 3 word. Okay, all right. And next, see this. This is direct addressing mode. When it is direct addressing mode, this address 1 itself the effective address. Now, this is indirect addressing mode. So, this address 2 is the address of effective address. Address of effective address. Okay. So, what is this meaning? By taking this address 2, we refer the memory to get the effective address. From that effective address, we are accessing the data. Is it okay? Indirect addressing mode is already known to you. Okay, direct addressing mode means address field itself contain effective address. So go to that respective location, read the data or write the data with respect to source or destination. Okay, all right. Now interpret this information in the format, this structure. First thing, instruction fetch. So compulsory 1 memory reference required. Okay, what is this memory reference? Opcode fetch. Instruction fetch state means first word accessing. So in the memory, first word always contain the opcode. You know the instruction storage in the memory. Instruction stored in the memory with opcode first. After that, rest of the information is stored with the little endian mechanism. So in the instruction fetch, 1 memory reference is required to fetch the first word from the memory. That first word itself contains the opcode of the instruction. Okay, now decoding takes place. At the time of decoding, CPU identify the length of instruction. Okay, this is the 7 word instruction. Because of 7 word instruction, to fetch the complete instruction, 6 more memory references required. Because of it is 7 word, already 1 word is fetched here. Okay, 1 memory reference. 1 memory reference means 1 word accessing. Okay, so this is a 7 word instruction that is detected after decoding the opcode. Okay, when the CPU detected the instruction length as a 7 word, immediately the remaining part of the instruction is fetched from the memory. Okay, in the 7 words, Already one word is fetched during the IF. So remaining 6 words going to be fetched from the memory after decoding. So that 6 memory references counted here. Okay, so total 1 and 6. Total 7 memory references to fetch the instruction completely from the memory. Very good. Next, processing started. What is the operation here? Operation is the data transfer operation. Because of data transfer, there is no need of the source to, and also no need of the processing the data. Data transfer operation does not require the source to and PD. Next, source. What is the source addressing mode? Indirect addressing mode. In the indirect addressing mode, first we are going to get the effective address. So here address size equal to 3 words. When 3 words address, then what is required to get the effective address? 3 memory references required to get effective address. 3 memory references required to get effective address. Because of address size is 3 words. That is very important here. So source here 3 memory references required. Why 3 memory references? Okay, address size is 3 word. Okay, to get effective address from the memory. After that, 1 memory reference is required to read data. Source, read data. Data size equal to word size. So data means word. Therefore, 1 data accessing is nothing but 1 word accessing. 1 word accessing requires 1 MR. Okay, so address size varies, depends on the system configuration. So here address size is 3 words. So to fetch the address from memory, 3 memory references required. Because of it is a indirect addressing mode. Clear na? Alright. Then come to the destination. What is the destination here? Destination is a direct addressing mode. Already effective address is fetched. Therefore, so directly you are going to write the data, 1 MR to write the data. So for this instruction, there is no need of, for this destination, already effective address is present in the instruction itself. Okay, that instruction is already fetched at the end of ID. Therefore, there is no effective address fetching again because of direct addressing mode. Okay, so indirect addressing mode means at the end of ID, address of effective address is fetched. But I want effective address. That is the reason 3 more memory references are counted here. Okay, students, I hope you understand this logic. Very important logic. Okay, so you may expect this kind of the questions in the paper, right? Because in the previous concepts, in a previous question papers, by default contain address size equal to word size. That's what indirect addressing mode is always taking 2 MR. 1 MR to get the effective address, another MR to get the data. Okay, if and only if address size equal to word size. But here address size is not equal to word size. When address size is varies, number of memory references varies in the indirect addressing mode. Okay, by default indirect addressing mode taking 2 memory references to get the data. 1 memory reference for effective address accessing, another memory reference for data accessing. If and only if address size is word size or address size is not given in the question. But in this question, address size is given. Address size is 3 words. So to fetch the effective address from the memory, 1 attempt we cannot get the 3 words. To get 3 words address, 3 attempts required, 3 memory references required. I hope you understand this logic. Okay, students, now count the total memory references required in the instruction execution. That means fetch cycle and execution cycle. That is the total time required to complete the instruction. Okay, count it. All of you, please count. 1, 6, 7, 7 plus 3, 10, 10 plus 1, 11, 11 plus 1, 12. So total 12 memory references required. So answer is 12 MR. How many of you given the right answer? Please respond. This is the analysis of the question. How many of you given the right answer? Please respond. 12 memory references required. Is it clear? All right. This is the analysis. Now I am showing you the question once again. This is the question. So answer is 12. Okay, students. Is your answer matched? Matched? Okay. If not matched, please verify the analysis once again. So where you did the mistake, please identify your mistake. Don't repeat that mistake again. Okay. Very good. Now see the next question. Students, just read the question. This is the next question which I am going to explain in the GTQ session. Okay, that is, consider the following code executed on a 2 nanosecond clock cycle CPU. They given 2 nanosecond clock cycle. CPU clock cycle given. These are the instructions present in the program. Okay, 50 load instructions, 40 store instructions, 80 arithmetic. Then this is the jump instructions. They given 50 jump instructions given. Okay, so total 50 plus 40 plus 80 plus 50. This is not a relative data. So here question contain the absolute information. First you should identify this. This is the absolute value, not a relative data. When it is a relative data, sum of the data is equal to 100%. When you are adding given data, that become 100%. Okay, that is the relative value. But here it is not a relative value, absolute value given. CPI, cycles per instructions, also given here. Very good. In the CPU enhancement, load and arithmetic instructions are enhanced with a respect to speed ups of 4 and 3. Load instructions are modified and arithmetic instructions are modified. After that modification, those two instructions are running with a respect to speed up of 4 and 3. Okay, performance gain of a CPU is. So we need to identify the performance gain. This is the question. Okay, so old system and a new system. Okay, old system characteristics are given like this, so that calculate execution time of the old system, and new system characteristics. After enhancement, new system behavior is different. So calculate the execution time of new system. After that, report the performance gain. Okay, so all of you please solve the question. Okay, do it fast. Solve the question. Okay, so here actually execution time formula is summation of IC subscript I into CPI subscript I whole multiplied with the cycle time. So this is the execution time formula. Everyone knows that. I indicates the type of instruction. Okay, now substitute the given information, calculate the execution time. Right. First take the old system. System old. Execution time of old system is equal to 50 instructions into 8 cycles plus 40 instructions into 6 cycles plus 80 instructions into 12 cycles plus 50 instructions into 4 cycles. They given count of instructions and also CPI into cycle time. Cycle time of the computer is 2 nanosecond. That is mentioned already. Into 2 nanosecond. Okay. So compute the value. All of you do the calculation. Compute the value and report the final value. Do it fast. Do the calculations. That is 3600 nanoseconds. This is the execution time of the old system. Okay. Okay. Now come to the new system. In the new system, load instructions are enhanced. Come to system new. Okay. Load instructions. Instructions speed up is equal to 4. Okay. Then what is the formula? Speed up S equal to execution time of old upon execution time of new. This is the speed up formula. How much performance is improved after the enhancement? Okay, S is the performance gain. So S equal to execution time of old upon execution time of new. So we want already S value given 4, old time. Okay, see this, a load instructions old time is 8 cycles divided by new time. So we want new. So execution time of new with respect to load instruction is 8 cycles upon 4. That is 2 cycles. There is a change in the ALU instructions, arithmetic instructions and load instructions. So load instructions are enhanced with a speed up of 4. That's what load instruction takes 2 cycles. Now CPI will be affected. Now arithmetic instructions, see this, arithmetic instructions takes 12 cycles, okay, but enhanced with a speed up of 3. Same thing here, arithmetic instructions. Arithmetic instructions speed up is equal to 3, that is given. Formula of the speed up is S equal to execution time of old upon execution time of new. So this is execution time of new is equal to execution time of old upon s. So this is 12 cycles upon 3. This is equal to 4. Okay. After the enhancement, arithmetic instructions CPI is 4 and load instruction CPI is 2. Now calculate the execution time. Calculate the execution time. Okay. There is no change in the store CPI and no change in the jump CPI. There is a change in the load CPI and arithmetic CPI because of in the CPU enhancement, load instructions and arithmetic instructions are modified. So there is no change in the rest of instructions. Now calculate execution time. Correct. So now execution time of a new system. Execution time of new system is equal to 50 instructions are load taking 2 cycles plus 40 instructions are store, there is no change in the cycles, plus 80 instructions are arithmetic, each instruction taking 4 cycles, plus 50 instructions are jump, there is no change in the cycles. So the total number of cycles multiplied with cycle time. Okay, cycle time is same but CPI is different, right? Do the calculations. Compute the value, report the value. Please verify. So that is 1720 nanoseconds. Okay, this is the execution time of a new system. Old system execution time and a new system execution time both are ready. Now report the performance gain. Performance gain S equal to execution time of old computer upon execution time of new computer. Okay, which system gain we want to calculate, that system execution time is denominator in the formula. Correct? Right. So 3600 nanoseconds upon 1720 nanoseconds. Do the calculations. 3600 divided by 1720, that is equal to 2.09. This is the answer. Performance gain of a system after the enhancement is 2.09. I hope you understand the analysis of the question. Also, you know the concept of this question. Okay, how many of yours answer is matching? Please respond. Okay, if not matching, you know what to do. If answer is not matching, please watch the analysis which I explained here. Okay, follow that. Where you did the mistake, identify that, but don't repeat that mistake again. Okay, very good. So answer is 2.09. 2.09. This is the speed up. Okay, so no need to take so much stress. Okay, just read the question with careful attention, identify the given data and also identify what they are expecting. Okay, just apply the formula and also apply the concept. You may get the answers. Okay, don't take too much tension. These all are the conceptual based questions. Okay, in our regular notes I already explained all the concepts which are related to the computer organization subject. Okay, you know that. Okay, so once you have that basic fundamental knowledge which I explained in the classroom, then you can easily answer all the questions which are related to computer organization and architecture subject. Without knowing the concepts, you are not even understand the question itself. Okay. When you don't know the question logic, how can you solve the question? So for the computer organization and architecture subject, concepts are very important. Okay, computer organization concepts are very important. When you know the concepts, you know the terminology. When you know the terminology, you can understand the question. When you understand the question, answer is present in the question itself. That's it. Okay, all right, this is the question and this is the way to solve the question. Bus clear? All right, let me give the next question. Yes, this is the next question. All of you, please read the question carefully. Question is on the screen. So please read the question. Try to understand the logic and solve the question. Okay, along with you I am also solving the question. At the end we are going to compare both of our answers. Okay, read the question. Okay, all right, now see the question once again. I am also reading. Consider a hypothetical CPU, that is sample CPU, which supports X, Y, and Z types of instructions. They given three types of instructions. Okay, right. X instruction is one address instruction. Okay, register reference. Y instruction is also one address instruction but memory reference. Z instruction is one address instruction but immediate instruction with 3-bit constant field. Very good. System supports 20-bit instruction. Instruction size is 20-bit. 64 registers and 4 KB memory present in the system. If there exist 120 X instructions, 254 Y instructions, then how many Z instructions are possible? This is the question. Okay, then all of you please analyze the question, give the right answer. Okay, everyone knows that this question is related to expand opco technique question. How you know expand opco technique? Whether the question suitable to that question or not, how you know? Because instruction size is fixed. Instruction formats are different. So different instruction formats designed with the same length, fixed length. Then we are using expand opco technique. Okay, in the question expand opco technique term is not there, but we supposed to use expand opco technique because different formats on a fixed length. Compulsory we are using expand opco technique. Clear? All right, fine. Now I am also solving the question. Please verify. These all are the fixed concepts actually. Computer organization and architecture subject is a static subject. Static subject in the sense all the terms are fixed terms. We cannot modify the terms. We cannot change the terminology of the subject. Okay, because computer is a real machine, designing is real designing, so we should remember that structure. So once you know the structure of the computer, then you can answer all the questions, because every question is a static oriented question. Okay, concepts are same, terminology is same, structure is the same, only numerical values are changed. Once you know the concepts, terminology, then you are in a position to answer all the computer organization and architecture subject questions. Very good. Okay, all right, come to this. Here what is given? Given is instruction size is equal to 20 bit, that is given. Next, instruction formats. Given. Okay, Z instruction, Y instruction, X instruction, X, Y, Z given. This is the one address instruction, but register reference. Y, one address instruction, but memory reference. Then Z, one address instruction, but immediate instruction. Yes. So three different formats given. So three different formats, but all the instructions are having the same length. So use the expand opcode technique. Different formats, all the instructions are having same size, fixed instruction. Then we are using the expand opcode technique. Different instructions are designed with a fixed length. Use the expand opcode technique. Very nice. Now, what is the X instruction? See this. X instruction format is opcode register reference. One address, register reference. So that address will contain register address. Y. One address, memory reference. Opcode address contain memory address. Then Z. Opcode one address, immediate. That is given, immediate field. Okay. Okay. I took the format, whatever it is given in the question. And after that, all the instructions are 20 bit. This is 20 bit. This is 20 bit. This is also 20 bit. 20 bit instruction. Alright. So now, number of registers, how many? 64 given. And memory capacity 4 KB. 3 bit constant field. Now see this. 64 registers. Therefore, register size is 6 bit. Okay, opcode size is 14 bit. Memory 4 KB. 4 KB means 12 bit memory address. Then remaining 8 bit opcode. Then immediate. They given 3 bit constant field. When 3 bit constant, 17 bit opcode field. Very good. So we just taken the instruction formats with respect to the question. Okay, alright. Next is what? Compare the opcodes. This is 14 bit opcode. This is 8 bit opcode. This is 17 bit opcode. So smallest opcode is primitive. So here Y is the primitive instruction. Next smallest is the derived. Okay, and the next smallest is the further derived. Like this, we are going to identify the primitive instructions, derived instructions, further derived instructions based on the opcode size. Okay, alright. After that, compare the primitive and derived. In the primitive, we have opcode and memory address. In the derived, we have opcode and register address. So, take the common parameters. So, opcode common. So, take as it is. Okay, address not common. Here 12-bit address, here 6-bit. Then what we need to do? From the 12-bit, take the 6-bit. From the 12-bit, take the 6 bits for the register address, and remaining 6 bits are merged to opcode. Okay, rest of the 6 bits merged to opcode like this. So from the 12 bits, here we taken the 6 bits and remaining 6 bits are merged with the opcode. Then only opcode size become 14-bit. Right. Now identify the derived and further derived. Okay, opcode register, opcode immediate. Take the common parameter as it is. Yes. Opcode required. Taken. Here address is 6-bit. Okay. Here address is 3-bit. So from the 6-bit address, take the 3 bits and assign to immediate. 3 bits are given here and remaining 3 bits are merged here. That's it. This is the expand opcode technique question which I already explained in the regular class notes. Okay. So primitive, derived, both are compared, taking the common parameter. Okay. Non-common parameters are appended to opcode field. Then only opcode size is increased in the derived instruction. Okay. Now compare the derived instruction with further derived instruction. Take the common parameters. Later, non-common parameters are appended to opcode field. Then opcode size increased in the further derived instructions. This is the logic of the expand opcode technique question. Everyone knows that. Okay, we did so many questions in our regular class notes. Okay, if you see the PYQs, previous year gate questions, this concept related questions are frequently asked questions. Okay, with 2 marks weightage. That's what carefully analyze the expand opcode technique concept and also solve the number of questions under this concept. In the exam, if this concept based questions are there, you are in a position to give the right answers within a less amount of the time because you already analyzed this concept in your regular practice. Okay, very good. Now come to the further analysis. First take the primitive. Format, that is opcode and memory address. Okay, what you have? 12-bit opcode and 8-bit 12-bit memory address, 8-bit opcode. 12-bit is the memory address, 8-bit is the opcode. This is primitive. So now identify the number of operations possible. Number of operations possible is depends on the opcode, that is 2 power 8. That is 256 primitive opcodes are possible. But how many are implemented? That is given here. So how many Y instructions are present? See this, Y instructions. 254 Y instructions present. Clearly given in the question. Yes, 254. 254 means here number of free opcodes equal to free opcodes after Y instructions. After Y instructions equal to 256 total possible, 254 implemented. Therefore, 2 free opcodes we have. So these free opcodes are used for the derived instructions. So fourth one, number of X instructions possible. possible equal to number of free opcodes into how many bits are merged here? 6 bits, 2 power 6. So this is equal to 128. So 128 X instructions are possible after implementation of 254 Y instructions. Okay, but according to the question, how many X instructions are already implemented? According to the question, 120 X instructions are already implemented. Correct? Now, number of free opcodes after X instructions is equal to 128 minus 120. That is 8. 120 X instructions are already present. That's what 8 free opcodes present. So these 8 free opcodes are used for the Z instructions according to question. So now number of Z instructions possible in the system is equal to free opcodes 8 into how many bits are merged? See that. From the X, 3 bits are appended to opcode, 3 bits, 2 power 3. 3 bits are appended, 2 power 3. So that is 2 power 6. That becomes 64. So 64 Z instructions are possible after implementation of 254 Y instructions, 120 X instructions. Okay students, so this is the way to solve the question by using expand opcode technique. So answer is 64. How many of yours answer is matching? You please respond. Okay, this is the analysis of the question. I ask you to solve this question along with me in parallel. Correct? So how many of yours answer is matching? Please respond. This is the question. Okay, that is the analysis. So number of Z instruction, Z type instructions possible in the system is 64. 64 Z type instructions are possible in the system after implementation of 254 Y type of instructions, 120 X type of instructions. This is the expand opcode technique concept based question. Hope you understand, right? Very good. Students, is the answer clear? Answer clear? No? All right. So I given the question. I also given the analysis of the question. Okay. Many of you given the right answer. Thank you so much, dear students. Thank you. Right. See the next question. All of you, read the question carefully and try to solve the question. This is the next question which I am going to explain in the GTQ 2024. Consider the following code executed on a 32-bit hypothetical CPU. Say this, 32-bit hypothetical CPU given. Code is stored in the memory with a starting address of 4000 base 10. So decimal address sequence given. Cycle time is 2 nanosecond. Okay. Each instruction on average takes 5 cycles to complete. So in this question, instruction execution time is already given irrespective of addressing modes. So here addressing modes are not matter, because question itself says on average each instruction takes 5 cycles to complete. Very good. Interrupt subprogram takes 20 cycles to complete. Interrupt subprogram taking 20 cycles to complete. This is the code given. In the code, see this, I1, I2, I3, I4, I5, I6, I7, I8. So total 8 instructions are present in the program. 8 instructions present. So every instruction taking 5 cycles. That is already given here. On average, each instruction taking 5 cycles. Interrupt subprogram taking 20 cycles. That is also given. So here fetch cycle, execution cycle, these are not matter. Length of instruction not matter. Addressing modes not matter in this question, because on average every instruction takes 5 cycles to complete. That is mentioned in the question. Next, in the program execution, see this. In the program execution, interrupt, INT, you know that interrupt. This is the interrupt. Interrupt shortcut is INT. If interrupt occurred during the execution of add instruction and mul instruction in the program. In the program, interrupt occurred during the execution of add and also during the execution of mul. You know that when interrupt occurred, servicing required. Very good. So at the time of executing the addition instruction, interrupt occurred. At the time of executing the multiplication instruction, interrupt occurred. See this, addition is the I3. Okay, at the time of executing the I3, interrupt occurred. So here interrupt occurred. Then mul is the I6. At the time of executing the I6 also, interrupt occurred. Is it clear now? Very good. What is the program execution time in nanoseconds? So we need to identify the program execution time. Clear? So this is the question. I explained the logic of the question. I hope you understand. So immediately you please solve the question. I am just waiting for a moment. Okay, you please solve the question. I explained the complete logic of the question. So you please solve the question. Do it fast. Are you solving or waiting for my analysis? Some of you are solving the question, some of you are waiting, right? Okay, let me solve the question along with you. Listen. Here, question requires the concept instruction cycle along with interrupt. Instruction cycle along with interrupt. Very good. This is the concept. So see this, fetch cycle, after this execution cycle, Okay. After this, checking for interrupt. Checking for interrupt. Okay. If interrupt present, then service the interrupt. After that, go back to fetch cycle. If interrupt not present, simply go back to fetch cycle without service. Yes, this is the concept required for this question. Dear students, if interrupt present, service the interrupt. If interrupt not present, directly go to the next fetch. This is the concept, okay? Alright, so now what we are going to do? We are going to execute the program. First I1 executed. Fetching I1 executed. No interrupt. Fetching I2 executed. No interrupt. Fetching I3 executed. After I3, interrupt present because of I3 is a add instruction. Now servicing required. This servicing taking 20 nanoseconds. Sorry, 20 cycles. Very good. Next, I4 executing. I4 fetching, I4 executing. There is no interrupt. I5 fetching, I5 executing. No interrupt. I6 fetching, I6 executing. Yes, interrupt present. When interrupt present, servicing required. So 20 cycles required to service. Okay. Alright. Next. I7 fetching, I7 executing. No interrupt. I8 fetching, I8 executing. No interrupt. You may have the doubt, sir, halt instruction executing infinite number of times. Yes, CPU point of view, halt is executing infinite number of times. But user point of view, halt is executing only once. Okay, so program execution time means halt is executed only once. That is user context. CPU context, halt is executed infinite number of times. Okay, very good. So now what is the program execution time? Now you calculate that. So total 8 instructions are present. Here program execution time. 8 instructions present into on average every instruction taking 5 cycles. Okay, plus 2 times interrupt occurred. 2 times interrupt occurred. Okay, so interrupt number of occurrences. 2 times interrupt occurred in the program into interrupt service time 20 cycles. Okay students, all right. So the total time, that is CPU cycle time, is equal to 2 nanoseconds, that is mentioned. Clear? Now calculate this. Calculated final value, please report. 40 cycles plus 40 cycles into 2 nanoseconds. This is equal to 160 nanoseconds. This is the answer. Please cross-examine the calculations. Students, is it clear? While executing the instruction, if interrupt occurred, CPU respond to the interrupt after completion of the instruction. At the time of addition, interrupt occurred. CPU respond to the interrupt after completion of addition. Okay, at the time of multiplication, interrupt occurred. CPU respond to the interrupt after completion of multiplication. Okay, all right. So answer is 160. This is the analysis. Let me show the question once again. This is the analysis. Okay, I hope you understand the analysis. Yeah, this is the question. In the question, options are there. Now we need to select the answer. 160 nanosecond. B is the answer, right? B is matching. Okay, students, clear? Very good. Now let me show the next question. Please read the question. This is the next question which I want to explain in the GTQ 2024. Consider 32-bit hypothetical CPU which supports instruction with 2 register operands, given clearly. 2 register operands, memory operand, and 2 immediate constant fields. 2 register operands, memory operand, 2 immediate constant fields. System supports 100 instructions. Okay, 60 registers with a register wide of 32-bit. What it means? Number of registers are 60. In every register, we can store 32-bit information. Okay, 4 MB RAM, 13-bit constant size. Okay, program contain 240 instructions. Number of bytes required to store the program is. How much storage space is required to store the program in bytes? This is the question. Okay, so this kind of questions we solved in our regular class notes. Also, this kind of questions present in the previous year's GATE papers. So that now we are going to solve the same kind of question. Question structure is same, but some small changes present. Numerical values are compulsory changed and instruction format is compulsory changed. Okay, concept is same, but question formulation, structure of the format different. Okay, so please try to understand the logic of the question and also solve the question, give the right answer. Please do it fast. So in this question, what they given? Instruction format given. It is a 32-bit CPU which supports instruction with. Okay, so you know every instruction by default contain opcode. Every instruction by default contain opcode. Opcode with 2 register operands. So register and also register. 2 register operands. Memory operand, and also 2 immediate constant fields, that is given here. Immediate constant fields, hypothetical format it is. So they given 2 immediate fields. This is the total instruction format according to question. Yes, this is the question. Clear? Now, system supports 100 instructions. So log 100 base 2. Log 100 base 2 means 7-bit opcode is there. Then number of registers 60. Log 60 base 2, that is 6-bit address. Again log 60 base 2, that is 6-bit address. Then memory log 4 megacells base 2, this is 22-bit address. Is it okay? 4 2 power 2 mega 2 power 20. Then immediate 13-bit immediate field. So each constant is represented with 13-bit size like this. This is the instruction format according to question. Therefore, instruction size equal to okay, do that. Add all those 7 plus 6 plus 6 plus 22 plus 13 plus 13. that is 67 bit. This is the instruction size. Very good. In this computer, instruction is designed with a 67 bit. Okay. So like this, how many instructions are there? 100 instructions are there. Instruction set means unique operations. 100 unique operations present in the CPU. Making use of 100 instructions, user developed the source code. That source code having 240 instructions. See this. System contain 100 instructions. System is having 100 instructions. By taking the help of 100 instructions, user developed the source code with 240 instructions. So number of instructions are 240. Okay. Then how much space is required to store the program in the memory? Okay. That is required in bytes. We want the program storage in bytes. This is very important. Okay. Students may take the wrong calculations in this. Okay. Where the student taking the wrong calculation? Directly what the students are doing is 240 instructions into each instruction 67 bit divided by 8, because question is expecting the program space in bytes. So 240 into 67 divided by 8. That may be the answer given by the student. That is wrong answer. Reason is memory is a byte addressable memory. See this? Memory 4 MB. 4 MB means cell size is byte. So in every cell we have only 1 byte space. So you may store only 1 byte information in one cell. Program stored in the memory, okay, instruction by instruction. So each instruction occupies how many cells of the space, that you need to calculate. Okay, alright. Now see this. Program size. They given program size equal to 240 instructions. Okay, storage. Okay, memory is a byte addressable memory, so here 8 bit, 8 bit, 8 bit, like this. These are the cells. Memory storage cells. In every memory storage cell, we have only 8 bit storage space by default. 8 bit, like this. Okay, so now when I store the instruction, this is I1, 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 I1. See this? 1, 2, 3, 4, 5, 6, 7, 8. 8 cells. 8 into 8, 64. But your instruction size is 67. So here one more cell is required. In that cell, we want 3 bits space and remaining 5 bits are wasted. Okay, I want only 3 bits. So that this cell is also counted for the next instruction. After storing the first instruction, we are storing the second instruction. So when you are storing one instruction, okay, 9 cells space required per instruction. For one instruction, 9 cells space is required. In that, 5 bits space is wasted. Let it be. That wasted space is not countable. Cell is countable. So in that space, we cannot accommodate the I2. Okay. So that every instruction taking 9 cells space. Like that 240 instructions are there. Therefore, program space equal to 240 into 9. Do the calculations. 240 into 9. That is 2160 cells. Okay. That is 2160 bytes. This is the answer. Dear students, I hope you understand this. Okay. Normally, students are taking the wrong calculations here. So because of your wrong calculations, you may select the wrong answer. Okay, so don't take the wrong calculations. Very simple concept it is. Memory is a byte addressable. Every cell is having 8-bit space. Instructions are storing one by one, instruction by instruction stored in the memory. So this is the way of storing the program. So space is 2160 bytes. Go back to options. Okay, select the right answer. 2160. Right answer is B. B is matching. Those who are taking the wrong interpretation, they may give the wrong answer. Okay, compulsory. That wrong answer is also present in the options. Wrong answer is also present in the options, but that is not correct. Correct answer is B, 2160. Okay, students, I hope you understand the same analysis. Okay, how many of your answer is matched? Please respond. Okay, if not matched, verify the analysis once again. Don't repeat the mistakes. Okay, fine. This is the question. All right, and this is the analysis. Okay, all right. See the next question. This is the next question which I want to explain in the GTQ 2024. This is also one good question. Let me see how many of you giving the right answer. Here in this GTQ session, I am going to explain different questions actually. These all are the different questions with the small tricks. Okay. So if you analyze these questions properly, you may get the complete imagination of the subject. Okay. Very good. See that. Consider what they mentioned. 16-bit CPU. Use it to execute the following code. System supports one-word opcode and two-word address. Very good. Again, you need to check this. Address size is 2 words. Very important parameter it is. 2 words address. Okay. Especially this address size is matter when you have the indirect addressing mode. When we have indirect addressing mode, obviously address size is matter. Very good. At the rate symbol uses indirect addressing, square brackets uses direct addressing. Very nice. Register R2 is designated as index register. R2 is the index register. Following code is used to execute in the CPU. This is executed in the CPU. Instruction follows standard syntax. What is standard syntax? First opcode, next destination, next source. Very good. Now, so total how many instructions given? I1, I2, I3, I4, I5, I6, I7. Total 7 instructions given here. Okay, right. Number of memory references. See this. Number of memory references required to access the data. Number of memory references required to access the data is. See, they want only the data accesses. Okay, we don't want the instruction access. Data access we want. Right? Now, where I1 to I6. I1 to I6 instructions are executed 5 times in the code. I4 to I6. See, I4 to I6. 4, 5, 6. Okay, 3 instructions are executed 5 times in the program. And remaining all instructions are executed only once. But I4, I5, I6. I4, I5, I6. 3 instructions are executed 5 times in the program. Now we are going to count the number of memory references. Okay, now see this. Actually, when I explain the instruction cycle, what you have? IF, ID, OF, PD, WB. These are the things. These are the 5 states. Source 1, source 2 and destination. Very good. This is the framework of the instruction execution. Is it okay? See this. All right. So here data accesses. Very important. Data access means operand access. Access belongs to read access and write access together. So here data access means here source 1 data, source 2 data. This is the data access. Data read access. Here read access present. Then WB. This is the destination. This is also data access. What access it is? Data write access. Very nice. Data read access, data write access. Very good. Fine. Now what we are going to do? Question is expecting only the data accesses. So here these data accesses are depends on the addressing modes. These data accesses are depends on the addressing modes. What is the source addressing mode? What is the destination addressing mode? Based on that, number of memory references are countable only for data. Okay, in this GTQ session, I already explained one question earlier. If you remember that question, there we are calculating the number of memory references to complete the instruction. To complete the instruction, fetch cycle time plus execution cycle time together we are counted. Okay, but in this question, we are calculating memory references only for data. Data accesses के लिए memory references required. So data access means operand fetch and write back. Okay, in the operand fetch, read access and write back, write access. Okay, they are not asking only read access. They are not asking only write access. When they are asking data access, we are counting read and write together. Clear? All right. So now identify the information. First question, first instruction. See this. Instruction 1, data transfer instruction. Square brackets indicates the direct addressing mode. Okay, so here source and destination. So instruction 1, only one MR required. This is the source. Okay, now instruction 2, come to this. Instruction 2, move R1, destination is register reference. This is what? At the rate, indirect addressing mode. Very nice. That is indirect addressing mode. Destination, register addressing, register reference not required. We want memory reference. So, source, I2, source is what? Indirect addressing mode. Indirect addressing mode means first we get the effective address. See this, address size is 2 words. Therefore, 2MR to get effective address. Okay, and 1MR to read the data. So total, because of indirect addressing mode, 3MR required to access the data. Get the effective address, access the data. Indirect addressing mode accessing 3MR. Okay, data accessing means don't count only 1MR. This effective address accessing is also part of your data accessing because of the indirect addressing mode. Indirect addressing mode के कारण first access effective address, then access data. These two are counting in the operand fetch itself. Operand fetch itself. But here address size is 2 words. That's what 2 memory references required to fetch the effective address. Clear? Very nice. Then come to the I3. I3 both are register addresses. Therefore, I3 no MR. डेटा एक्सेसिंग के लिए MR नहीं चाहिए. Then I4, see this. It is move instruction. R0 is the source. Again, see this at the rate. Indirect addressing mode. So here, I4. Destination requires. Indirect addressing mode is destination. So here 2 MR to get the effective address and 1 MR to write the data. To get effective address and here to write data. Fine. Then I5. I5 is the, see this, destination addressing mode is direct addressing mode. So I5. Destination D. D means destination, 1 MR to write the data. Then I6. Again, source addressing mode is the, see this, source 1 addressing mode. One thing. I5 is the destination direct addressing mode. So 1 point please. I5 is like this. I5. Add means address loaded with address plus R1. So here 1 MR and again here 1 MR. Yes. This is the data manipulation instruction. Therefore, destination and source 1. 1 MR. To read data. This is important, dear students. Fine. Now I6. See I6. I6 is the multiplication division instruction. So what is this? R3 loaded with R3 divided by at the rate of address. So here this is the register reference. This is indirect addressing mode. Indirect addressing mode means address fetch 2 memory references because address is 2 word. Then data fetch 1 MR. This is. So I6. Instruction I6. See this. I6 instruction. Source 2. We want source 2. 2 MR and 1 MR. 2 MR for to get effective address and 1 MR for to read data. That's it. Then I7. See this. I7 is the move instruction, index addressing mode because R2 is the index register. So here I7 is like this. I7 instruction, M of 4000 plus R2 is updated with R3. So here memory references. How many memory references? Only 1 MR. We are counting only memory references. 1 RR, 1 ALU, 1 MR. So here I7 requires I7. This is the destination. Requires 1 MR. For what purpose? To write data. Is it clear? Very good. Alright. So now total number of memory references. You just see. I1, I2, I3, I4, I5, I6, I7. Then you just accumulate total here. I1, I2, I3, I4, I5, I6, I7. Okay, I1, 1 MR. I2, 3 MR. data access I am talking. I3 0 MR, I4 3 MR, I5 2 MR, I6 3 MR, I7 1 MR. But here I4, I5, I6 running how many times? They given in the question 5 times in the code into 5. 5 times. Okay. So total execution time equal to number of memory references equal to 1 plus 3 4, 4 plus 1 5, 5 MR plus then this is 3 plus 2 5, 5 plus 3 8, 8 MR into 5 times. Okay. So this is equal to 45 memory references. Okay students. Total 45 memory references are required to access the data. Only data access point of view, answer is 45. Okay. So this is the analysis. Students, I hope you understand this. Here what you realize is this is only the data access. Data access means operand fetch and WB. These two states memory references are countable. These two states memory references are depends on the addressing mode. Addressing mode. Whenever indirect addressing mode is given, compulsory address size is very important parameter to count the number of memory references. Okay, in this question address size given 2 words. That's what effective address accessing takes 2 memory references with respect to the indirect addressing mode. Okay students, I hope you understand the analysis. Okay, if your answer is not matching, don't worry. Okay, you please analyze the question solution which I explained here. Okay, try to understand where you did the mistake. Maybe your mistake is address size. Okay, many students are taking the indirect addressing modes means 2 MR, 1 MR for effective address access, another MR for data access. Okay, so that is true if and only if address size is not given or address size is 1 word. But in this question, address size is exclusively given 2 words. When address size is 2 words, to get effective address from the memory, obviously 2 memory references required because of it is a indirect addressing mode. Okay, only in that point students may get confusion, student may give wrong answer. Okay, if you realize that problem or that kind of mistake in this question, okay, you never do the same mistake in future. Okay students, all of you carefully analyze this question and try to give the right answer always in future questions also. Okay, all right. This is the analysis. Just I am showing you the question once again. This is the question. Analysis given, question also given. Okay, all right. Now I am going to show the next question. You just see the question. Next question which I want to explain is pipeline question. Watch this. All of you see the question. Consider 6-stage pipeline IF, ID, OF, EX, MA, WB with 3 nanosecond clock used to execute the following code. Okay, so this is the code given. All instructions are spending one cycle on all the stages, but load takes 3 cycles on MA stage. Add and sub takes 2 cycles on EX stage. Amount of time saved to execute the code with operand forwarding over without operand forwarding is. Okay. Actually, students, I explained a lot of questions. Okay, number of questions which are related to the pipeline in our regular class notes. Everyone knows that. In the regular class notes, we have the questions. Okay, which are related to pipeline. Okay, I hope you practice or you analyzed all those questions, you solved all those questions multiple times. Not only in the regular notes, okay, we have the pipeline questions in our workbook, Made Easy workbook, and also there are questions in the PYQ. I ask you to solve PYQ questions and workbook questions, class notes questions. Okay, in your regular practice, I hope you completed all those questions multiple times. So no need to explain the basic fundamental questions in that area. That's what straightforward I'll come to the question which is related to data dependency, operand forwarding question. Okay, you just see the question that is already present on the screen. Okay, read the question. In the gate paper, this kind of the question usually 2 marks question, 2 marks weightage question. Okay, read that. Consider 6-stage pipeline. Clearly they given 6-stage pipeline. IFID, OF, EX, MA, WB. Instruction fetch, instruction decode, operand fetch, execution, memory access, write back. They mentioned. With 3 nanosecond clock, use it to execute the following code. This is the code given. Total 5 instructions present. Fine. All instructions are spending 1 cycle on all stages, but load takes 3 cycles on MA, add and sub takes 2 cycles on EX. Amount of time saved to execute the code with operand forwarding over without operand forwarding. Okay, right. I explained a number of questions in our regular notes which are related to this operand forwarding technique. Just to see that. So here, first what we need to do is take the pipeline stages IF, ID, OF, EX, MA, WB. 6 stages given. I1, I2, I3, I4, I5. 5 instructions given. Like this. Later, all instructions spending 1 cycle on all stages. Like this. IF, ID, OF, okay, WB. These are taking 1 cycle. Fine. Next, load instruction spending 3 cycles on MA. Here, I1 is the load, I4 is the load. I1, 3 cycles on MA, I4, 3 cycles on MA. Okay, remaining 1 cycle. Like this. Next, add take 2 cycles, sub takes 2 cycles on EX. I2 is the add, I3 is the sub, I5 is the add. So they are taking 2 cycles. Okay, 2 cycles on EX, 2 cycles on EX, 2 cycles on EX. Remaining 1. Yes. This is the table formulation based on the given information. Okay, everyone knows that. Total 6 stages, 5 instructions. According to given information, how many cycles are required at each stage that we identified in the table. Very nice. Now we need to take the dependencies. Verify the dependency. Instruction 2 input. Instruction 1 output. Matching? Yes. Then you can say I2 is dependent on I1. Okay. Next, instruction 3 input, instruction 1 output, matching? Yes. So I3 dependent on I2, like this. Then instruction 4 input, R6. Okay, memory 4 plus R6, not matching, so no dependency. Instruction 5, yes, this is matching. So instruction 5 dependent on instruction 4, very good. So here instruction dependency is also identified. When there is a dependency, there may be a stalls possible. Okay, with operand forwarding, without operand forwarding also, there may be a possibility of the stalls. You may have doubts, sir, with operand forwarding, how stalls are possible? Yes, when instructions are having the load instructions, program is having the load instructions, then compulsory there may be a possibility of the stalls that I explained in the risk pipeline also. Even you have a operand forwarding technique. Okay, right. So to solve this question, you may have the different methods, right? We may solve this question by drawing the space-time diagram. Also, we may solve this question directly by watching this table. There are two methods are there to solve this question. Okay, by drawing the space-time diagram or cycle diagram, you may solve this question, or directly by looking at the table, you can identify the number of stalls and solving the question. I already explained these two methods in our regular class, you know that. Whichever the method you feel convenient, take that method and solve the question. Okay, all of you, please do it fast. Up to this it is clear. So please solve the question. I am just waiting for your answer. Because operand forwarding concept is very important concept in the computer organization subject. So you please solve this question. I am waiting for your answer. Do it quickly. Students, have you completed the analysis? What is the answer? It may take more time, right? Okay. So first let me explain the optimized method to solve this question. After that, I'll also explain the manual procedure to solve the question by using the space-time diagram or cycle diagram. Okay, all right. First thing, optimized method. Okay, with operand forwarding, without operand forwarding. We are using program execution with operand forwarding and also program execution without operand forwarding. First, let us take with operand forwarding. With operand forwarding technique, how to execute. Total number of instructions given is 5. So I1, I2, I3, I4, I5. So I1 is independent, there is no stalls. So there is a stalls present in the pipeline due to the dependent instructions. Okay, so I1 is independent, there is no stalls. Fine. Total number of inputs are 5. 5 inputs plus we need to identify the stalls. Stalls depends on the dependency condition. Now see this. I2 dependent on I1. So you know that dependency detected in the ID stage. Very good. But operand fetch, data access will happen in the OF stage. When I explain the risk pipeline in your regular class notes, operand access, operand reading, operand fetching happened in the ID stage itself. So ID stage overlapping with EX stage. So by using that risk pipeline, I explained the concept of the pipelining. Okay, but this is the hypothetical pipeline. In this hypothetical pipeline, operand fetching happening in the separate stage. Okay, so where the operand fetch is happened, That stage is very important for the data dependency condition. What is data dependency? Wrong data accessing. When the wrong data enter in the pipeline after execution of the program, output is missing. So we need to identify the data accessing in the pipeline. That is most important. Data accessing is very important. Whether data is wrong data or right data which we accessed, that is important. So operand fetching is important in the data dependency condition. So in this pipeline, operand fetching takes place in the OF stage. Data dependency detected in the ID stage, operand accessing takes place in the OF stage. Okay, so operand accessing stage is important. Clear? All right. See this. So here operand fetch is overlapping with EX stage. Very good. Now see this. I1 is a load instruction. So load instruction output is present in the MA buffer. So when the I1 data is available in the EX buffer, there is no stall. But here EX buffer does not contain the data. It may contain the effective address. Then where the data present? After MA. Therefore one cycle overlapping, extra 3 cycles are the stalls. These are the 3 stalls. This is the concept. Operand fetch overlapping with EX stage. If data is available in EX stage, there is no stall. Okay. But here data present in MA stage. So one cycle of EX, one cycle of OF overlapping. Extra 3 cycle stalls. Very nice. Then come to the I3. I3 dependency detected in the ID. Operand fetch takes place here. Okay, this operand fetch overlapping with EX. So I2 is a ALU instruction so that output is present in the EX stage. But you know, this is one cycle, this is 2 cycle. One cycle overlapping, extra 1 stall present. Because EX taking 2 cycles, therefore 1 stall present. Very nice. Then I4, dependency detected in ID. So it is not dependent. I4 is not dependent. Very good. So directly we'll go to the next OF. But OF overlapping with EX. It is not dependent. Still it is waiting because EX is taking 2 cycles. Okay. So this I4 is waiting for stage. This is called as the structural hazard. Structural dependency. You can say structural hazard. So I4 is not waiting for data. I4 is waiting for stage. Okay. OF overlapping with EX. When it is one cycle, EX also one cycle, there is no stall. But here it is one cycle, then EX taking 2 cycles. It is not waiting for data, it is waiting for stage. So this is the one stall. This one stall is called as the structural hazard. This is the structural hazard. Okay, students. Then I5. See that. I5, data dependency detected in the ID stage. Operand fetch takes place here. So this operand fetch, okay, overlapping with EX stage. But here EX does not contain the data. It is the effective address because I4 is the load instruction. Because I4 is the load, this is effective address. Then where the data present? Data present in the MA buffer. So MA taking 3 cycles. Therefore, here 3 stalls. Very good. Plus, now come to the I5. I5, when all stages are taking one cycle, there is no problem. See this? It is taking 1 cycle, this is taking 1 cycle, 1 cycle, 2 cycle, 1 cycle, 1 cycle. So here, see this? When every instruction taking one cycle, there is no stalls. But I5, EX itself taking 2 cycles. 2 cycles means 1 cycle stall is present. So here plus 1 stall. Got the point? Because of EX is taking 2 cycles. Every stage supposed to take one cycle. That is the pipeline characteristic. Pipeline means every instruction spending one cycle on every stage. Then only inputs are moving in a synchronized manner. If any stage is taking more than one cycle, stalls are coming there. Okay, alright. So total how many stalls present? 3 plus 1 4, 4 plus 1 5, 5 plus 3 8, 8 plus 1 9, 9 stalls present. So here n equal to stall itself a input. Okay, stall itself a cycle. Every pipeline cycle is equal to one input. So that 5 plus 9, 14 inputs present. So here 14 is a finite value. 14 is a finite value. Therefore, execution time equal to k plus n minus 1 into Tp. So this is equal to k 6 stages plus n 14 minus 1 into cycle time of the pipeline. What is the cycle time given? 3 nanosecond clock cycle time. Okay, this is 3 nanosecond. This is 20 minus 1, 19 into 3. That is 57 nanosecond. This is the execution time of the pipeline with operand forwarding technique. Okay, students, you know this. Execution time of the pipeline with operand forwarding technique. Now I am giving you execution time of the pipeline without operand forwarding technique. Carefully watch this. Without operand forwarding. Okay, number of inputs I1, I2, I3, I4, I5. I1 is the independent instruction. There is no stall. Okay, dependent instruction creates the stalls. Okay, so here I4, one structural hazard. There is no problem. One stall. This is the structural hazard. Without operand forwarding is not affected with or without operand forwarding is not affected with a structural dependency. So इसमें problem नहीं है. Then I2 data dependency, I3 data dependency, I5 data dependency. Without operand forwarding means we are accessing the data after completion of the instruction. Okay, so in the next cycle, after completion of the instruction, in the next cycle, we are accessing the data. You know that. Now see this. Actually, I1, verify this. I1 is independent, I2 dependent. So dependency here overlapping with EX. Dekhna? So here, if data is available here, there is no stall. Without operand forwarding means we want data here. But where we are getting the data? After WB, you are getting the data. Here you may get the data. So 3 plus 1, 4. 4 plus 1, 5. So total 5 stalls. Without operand forwarding means read the data after write. After WB, in the next cycle, you are reading the data. So that's what 3 plus 1 plus in the next cycle. Again 1. Total 5 stalls. These are the 5 stalls. Clear? And next I3. This is overlapping with the EX. Okay, one cycle overlapping. Okay, extra cycles. Here 1 cycle plus 1 2 plus 1 3. In the next cycle you are reading the data. Here you are reading. So that from this 1 plus 1 2 plus 1 3 plus 1 4. So these are the 4 stalls. Then I4 is a structural hazard. It is not waiting for data. That's what one stall is, the structural hazard. Then I5 is overlapping like this. Okay, see this I5 overlapping. But here OF overlapping with EX. But we are getting the data after completion here. Data available in the next cycle. Here we have data. So 3 plus 1 4, 4 plus 1 5. These are the 5 stalls. 5 stalls. Okay, but after that, you see this EX taking 2 cycles. Now, every stage is taking one cycle, there is no stall. If any stage is taking more than 1 cycle, they are the stalls. So here EX taking 2, therefore 1 data stall is there. Extra time, 1 stall. 1 stall for execution of the I5. Okay, 5 stalls for data accessing stalls, and this 1 stall is the execution time stall here. So total number of stalls, how many? 5 plus 4, 9, 9 plus 1, 10, 10 plus 6, 16 stalls. So n is equal to 21. This is the finite value. Okay, now execution time. Execution time equal to k plus n minus 1 into Tp. So k value 6 plus 21 minus 1 into 3 nanosecond. So this is equal to 26 into 3. That is 78 nanoseconds. Okay, students? 78 nanoseconds. Now, how much time is saved? Previously, what is this execution time? 19 into 3. This is 57, no? Okay, time save equal to 78 minus 57 nanoseconds. Okay, report the value. 21 nanoseconds. Okay, students, this is the way to solve the question without drawing the space-time diagram. Okay, this kind of the method I already explained in the regular class notes. Everyone knows that. Okay, how I explained the optimized method without drawing the space-time diagram in regular notes. The same method I used in the question. Okay, wherever we want the data, that is matter. Okay, so in which stage we want the data, where the data is available. With respect to that, you need to find out the stalls. That's it, simple logic. In which stage we want the data, in which stage data is available, that difference is the stall. Okay, students, I hope you understand this logic with operand forwarding, without operand forwarding. So let me explain same concept by drawing the space-time diagram. If some students are not getting the concept, then I will explain the concept with space-time diagram. Okay, right. Let me draw the space-time diagram. Cycles. Clock cycle 1, clock cycle 2, like this. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, like this. These are the clock cycles. Total 5 inputs are there, right? Yes, these are the 5 inputs. I1, I2, I3, I4, I5. This is the with operand forwarding. Let us see without operand forwarding. CC1, CC2, 3, 4, 5, 6. without operand forwarding cycles. I1, I2, I3, I4, I5. Okay, students. So without operand forwarding, how to execute the program by using the cycle diagrams, that I will explain now. This is a manual procedure. Okay, without drawing the cycle diagram, how to solve the question, that I already explained, that is optimized method. So whichever the method you feel convenient, you take that method to solve the exam based question. Very good. Come to this. First, instruction IF, ID, IF. Next, OF, ID, IF. This is the overlapping execution. You know that. Now, EX, OF, ID, IF. So, you know, Thomas law algorithm, here it is detected. Now, we want data here. Data we want here. Now, this is overlapping with EX stage. But EX stage does not contain the data because I1 is the load instruction. Then where the data present? MA. MA taking 3 cycles. Here data present. So this data is forwarding here. Up to that it is waiting on OF like this. Then this is waiting on ID. This is waiting on IF like this. Okay. Next, this is moving to WB. Now this is coming into EX. Now this is coming into OF. Then this is coming into ID, and next instruction is fetched like this. Okay. Right. Now already here Thomas law algorithm is detecting the dependency. We want data here. Okay. So this data available in the EX buffer. Here it is available. 2 cycles. Here it is available. Here it is accessing. So OF, this is ID, this is IF. Next, moving into MA, this is the EX, this is the OF, this is the ID. Now, Thomas law algorithm standing here, na, there is no dependency. Dependency not present. But OF is waiting for what? This is matter. This is moving into WB. This is taking EX. Because of stage is busy. This stage is busy. So this is waiting on OF. So this is called as the structural dependency. This is the stage busy. Because of stage is busy, your instruction I4 waiting here. This is the stall. Structural dependency. Okay. After that, it is moving to where? MA. Okay. This is the EX. And this is the OF. Okay. So you tell. Thomas algorithm detected here. Data we want here. Okay. But data is not available in EX. Data available in where? MA. So this is WB, MA taking 3 cycles. After 3 cycles, data available. So up to this, it is waiting on OF. Okay. Next, WB. After that, EX. See, EX is not taking 1 cycle. It is taking extra cycle, na? Extra. Then MA. Then WB. So total how many cycles required? 19 cycles. Bus. So without drawing the space-time diagram, we get 19 as the number of inputs. K plus n minus 1. Number of cycles. K plus n minus 1 cycles are 19. Multiplied with cycle time, we get the value. That is the execution time with operand forwarding. Now this is the execution time without operand forwarding. See this. IF, ID, IF. This is what? OF. This is ID, IF. Okay. Next EX, OF, ID, IF. Now see this. Here data dependency detected. So data we want. So when data required, it is waiting until completion. So MA, 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 okay, WB, then OF. Up to that it is waiting on OF. This is waiting on ID. This is waiting on IF. Okay, so reading the data after write. Right, next point. This is EX. This is OF. This is ID. This is IF. Now Thomas law algorithm detected data dependency, OF. So first complete this. Say this, complete this. EX, MA, WB. Then read it. OF. Here OF. Up to that, this is waiting on ID. This is waiting on IF. Very nice. Fine. Okay. So next one. This is moving into where? OF. Next EX. This is OF. This is ID. Now Thomas law algorithm is standing here. Data dependency not detected. No data dependency. But it is waiting for what? Stage. EX. So it is waiting for stage. Stage is not free. That's what waiting. This is called as the structural dependency. Okay. Next. This is MA. This is the EX. This is the OF. Okay. Now Thomas law algorithm detected here. Data dependency detected. We want data. So first complete the instruction. MA, 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 WB. After completion, reading the data, it's waiting. Operand fetch. After that, EX. See, EX itself taking 2 cycles. Yes, 1 cycle here. MA, WB. Very good. Okay, total how many cycles? 26 cycles. Which we already calculated without drawing the space-time diagram. Then stalls counting. You just count the stalls now. See, these are the stalls. MA, MA, MA. Yes, these many. 1, 2, 3, 4, 5. Okay, for this. These are the stalls. 1, 2, 3, 4. Okay, for this is the stall. Okay, for this, these are the stalls. Count this. Okay, and this is also extra cycle. Okay, students. So, without drawing the space-time diagram or with drawing the space-time diagram, we know how to calculate the execution time. So, here time save equal to 26 minus 19 cycles. This is 7 cycles. Okay, cycle time is 3 nanoseconds. 7 into 3 nanoseconds. That become 21 nanosecond. This is the answer. 21 nanoseconds time is required to execute the program with operand forwarding over without operand forwarding. I hope every student understand the logic of this question. This is a nice question, 2 marks weightage question. Okay, I explained the analysis with the optimistic manner and also with the manual approach. Optimistic means without drawing the space-time diagram, solving the question. Manual means with drawing the space-time diagram, we are solving the question. Both the methods I explained. I hope you understand the same. So answer is 21 cycles are saved. Very good. Okay, fine. Fine. The next question. Students, this is the next question which I want to explain in the GTQ 2024 session. Okay, all of you see the question. This is the question which I want to explain in GTQ 2024 related to cache memory design. Again, in our regular class, I explained the cache memory concepts in detail, and also we solved number of questions in the cache memory area. Okay, so you already analyzed class notes questions, workbook questions, PYQ questions. Apart from those questions, see this question as a GTQ question. Okay, all of you read the question, try to understand the logic and solve the question. Okay, now see this. Consider direct mapped cache which contain 4 lines with a line size of 8 bytes. CPU refers the following main memory 6-bit address data. Main memory address 6-bit address given in decimal format P, Q, R, S given. Okay, so now this is the 6-bit address now. Main memory address equal to 6-bit address. Okay, so P, what is that? 17 base 10. Okay, if you see the binary 0, 1, 0, 0, 17, right? 0, 1, 1, 2, 4, 8, 16. Then Q, 14, base 10. Then 6-bit 0, 0, 1, 1, 1, 0. This is 14, correct? 1, 2, 4, 8, 14. Then R, they given 21 base 10. Okay, now what is the binary code of that? 0, 1, 0, 1, 0, 1. 1, 2, 4, 8, 16. 16 plus 4, 20, 20 plus 1, 21. Then yes, 42 base 10. What is the address? 6-bit address 42. 42 6-bit address is 101 010. Okay, see this 2, 8, 10, 32, 42 total. So this is the address given, main memory address data, PQRS, 4 data elements, addresses given in the decimal, converting decimal address into binary. How many bits of binary address required? That is given in the question, 6-bit memory address. So I converted the total decimal address into 6-bit binary address ready. Very nice. During the program execution, CPU refer the main memory data in this sequence. Yes, this is the sequence. This is the order. In this order, CPU referring the data. Okay. At the time of executing the program, first CPU refer the P data, next Q data, R data, S data. Okay, R, P, Q, S, P, R. Which of the following statements are correct? We need to identify the correct statements. Assume cache is initially empty. Assume cache memory is initially empty. Okay, so these are the options given. So which of the following statements are true statements? That we need to identify. Okay, all right. So now see the cache characteristics. This is the main memory address. Now go to the cache memory. Direct mapped cache. This is a direct cache. Okay, given. Number of lines also given. Number of lines are 4. Okay, then what is the block size? Block size equal to 8 bytes. Okay, right. So according to this, we need to identify the address format. Direct mapped cache address format is what? Tag, line offset, word offset. So word offset log 8 base 2 3-bit. Okay. Then 4 lines, therefore 2-bit. Okay. Then this is the 6-bit address. So 1-bit tag. This is the point. Is it clear? 3-bit, 2-bit, 1-bit. Now interpret this. These all addresses, you please interpret in this format. In this interpretation, last 3 bits, see this. Last 3 bits indicates the word offset. This is the word offset. Okay. Next 2 bits indicates the line offset. Yes, this is the line offset. And remaining bits are the tag. Okay. Very good. Now see this. When the tag is same, line offset. See, this is the 10 line offset. Line 2. This is the 10 line offset. Line 2. So these 2 blocks present in the same line. At the same time, see the tag. This is tag 0. This is also tag 0. What it means? P and R both are present in the same block. Okay. Tag is same. P tag and R tag. Data P, data R. Tags are same. Line offset is also same. That means P and R data elements are present in the same block. Here P and R data elements are in the same block. This is first thing. Both are present in the same block, but their word offset is different. See this. P and R both are present in the same block, but they are not same data elements. Word offset different. Word offset is different. Okay, fine. Now come to the next thing. Dear students, next is what? Q. Q line offset is 0, 1. R line offset is 0, 1. So these two are present in the same line. These two are present in the same line. But a tag is different. Tag is different. What it means? Q and S are data elements are present in different blocks. Different blocks. But both are mapped to same line. Same line, one at a time. Both are mapped to same line, one at a time. So that one is replaced by another. Is it clear? Line offset is same, tag is different. So that they are the different blocks, but both are mapped into same line. So one is replaced by another. So one is replaced by another, one is replaced by another means what? Thrashing may be possible when CPU referring the Q and S continuously. When CPU referring Q and S frequently, there may be a thrashing in line 1. When CPU referring the P and R continuously, there is no thrashing. That is advantage, because P and R both are present in the same block. Once block is copied and rest of the time P and R present in the same block. Okay. So only thrashing occurred in this program when CPU referring the Q and S frequently. This is the information what I identified after decoding the question information. After decoding the question data, this information we realized. Okay, right. Now come to the statements. What is the first statement given here? See this, first statement is P and S, both of the data elements, P and S, both of the data elements are present in the same cache block. This statement is true. Yes. Sorry. P and S na. P and R both are present. P and S both are not present. This is false. See this. P and S, right? They given. But here P and R both are present in the same block. But what the question says? P and S both are present in the same cache block. That is false. Next, in this statement, P and R both are present in the same block. Yes, this is true. First statement is false. Second statement is true. Now come to the third statement. Thrashing occurred. You know thrashing. Thrashing occurred when CPU refer Q and S data elements. Yes. See, this is the order. In this program, Q, S. Yeah. When CPU referring the QS continuously, there is a thrashing present. Yes. Thrashing occurred. This is also true. True statement. Very good. Then after that, hit ratio of the code, hit ratio of the program is 0.5. Now see, what is the hit ratio calculation? How to calculate the hit ratio? Okay, now see this. What is the order that you need to identify? This is the direct mapped cache 0, 1, 2, 3. Okay, cache is initially empty. Very good. Now first, CPU referring what? P is miss. Okay, so P is mapped to which line? P is mapped to line 2. So P came here, line 2. Then after this, CPU referring the Q. Q is also miss. Okay, Q mapped to which line? Q is mapped into line 1. Yes, here. Q came here. Fine. Next. CPU referring what? R. R is hit. Present in the same block. So here in this block, R is also present. Both are in the same block. That is hit. Next, S. S is miss. So because of S is miss, Q is replaced by S. Then R. R is hit. R is hit. P is hit. Okay, then Q. Q is miss. When Q is miss, S is replaced with Q. Then S. S is miss. When S is miss, Q is replaced with S. Then P hit. Then R also hit. Then what is the hit ratio? Hit ratio equal to number of hits upon total number of accesses. 1, 2, 3, 4, 5. 5 hits divided by number of accesses. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So hit ratio is equal to 0.5. Okay, students. So here hit ratio of the code is 0.5. This statement is also true. Hit ratio is 0.5. True statement. Okay. So when you see the solution, question analysis, this is the analysis of the question. First, main memory address is 6-bit. So given decimal addresses converted into the binary 6-bit address. Cache memory is direct cache. So physical address is interpreted into address format. According to that, you can decide which address present in which line. Whether elements are present in the same block or elements are present in the different blocks. So we identified this matter. After that, calculated the hit ratio like this. Okay, with this information, we are moving back to the question. Which of the following statements are true? Okay, what are the following statements are true? B is true, C is true, D is true. So first statement is false. Okay, and remaining all are matching. So right answer is B comma C comma D. This is the right answer. Okay students, I hope you understand the question analysis. Okay, all right. So in the cache memory area, you may have so many questions which we already covered in the regular running notes, okay, online test series, workbook and PYQ. Apart from those questions, here I am taken this question as a GTQ 2024 question, okay, from the direct mapped cache. I hope you understand the same question and you know the analysis of that question, okay. Also you given the right answers. I may expect like this. Whether you given right answer or not, I really don't know. Okay, if you given right answer, concept is hit. If your answer is not correct, okay, there may be a mistake in the analysis. You please cross examine the analysis. Okay, identify the mistake. Don't repeat that mistake in the future paper. Okay students, all right. So these are the questions which I want to explain in the GATE 2024 GTQ session. I hope you enjoyed the session. Okay, I hope you realized all the concepts which I explained in the computer organization and architecture subject, and also you realized all the questions which are related to the COA subject concepts. Okay students, all right. Thank you so much my dear students. All the best and God bless you all. Thank you.